In the vast Pacific Ocean, a concrete dome sits silently on a remote island, holding one of the world's most dangerous secrets. This isn't just any ordinary structure. It's cracking, leaking, and rapidly becoming uninhabitable as ocean waters rise around it. Inside lies 105,000 cubic yards of radioactive soil and debris from nuclear weapons testing, measured during the 1977 to 1980 cleanup that cost 6 servicemen their lives and left hundreds more with radiation-induced cancers. As we enter 2025, scientists are sounding unprecedented alarms about the high levels of plutonium-239 still trapped inside. The Marshall Islands Cactus Dome has transformed from a containment solution into what experts now call a nuclear time bomb, threatening the entire Pacific ecosystem. The structure that was supposed to provide permanent protection is now failing in ways no one anticipated. The concrete tomb that's falling apart. Built to contain nuclear waste for eternity, the dome now reveals the fatal flaws in its construction with each passing storm. The 2025 structural assessment reveals a dome in severe distress, with 187 of its 357 concrete panels showing significant deterioration. These aren't minor surface blemishes anymore. The concrete slabs that once fit together like a giant puzzle now display gaps large enough to slip a hand through. Water stains streak down the dome's surface, marking where Pacific storms have repeatedly battered the structure over nearly 5 decades. The concrete itself tells a story of miscalculation. When construction began in 1977, engineers used standard Portland cement mixed with local coral aggregate. This seemed practical at the time, but local materials introduced chlorides that accelerated corrosion within the concrete matrix. The dome's 18-inch thick walls were designed to withstand tropical storms, not the supercharged hurricanes that climate change has unleashed across the Pacific. Each major storm system brings winds exceeding 135 miles per hour in recent hurricanes, creating pressure differentials that flex the concrete beyond its design limits. Salt water has proven to be concrete's most relentless enemy. The Pacific Ocean's corrosive mixture has spent decades penetrating the dome's porous surface, with chloride ions attacking the steel reinforcement bars embedded within the concrete, causing them to expand as they rust and crack the concrete from within. Vegetation has discovered these weaknesses and exploited them mercilessly, with coconut palms and invasive shrubs taking root in the dome's cracks, their expanding root systems creating hydraulic pressure that splits concrete panels apart. The dome's original specifications assumed a stable climate with predictable weather patterns. Engineers calculated stress loads based on historical data from the 1950s and 1960s, when Pacific storms were less intense and temperature variations more moderate. They never anticipated the thermal cycling that now occurs daily. Morning temperatures of 78 degrees Fahrenheit give way to afternoon highs exceeding 95 degrees, causing the concrete to expand and contract repeatedly. This constant movement has opened hairline fractures that now measure several millimeters wide. The dome's trapezoid panel design, once considered innovative, has become a structural liability. Each panel relies on its neighbors for support, creating a system where failure in one section compromises the entire structure. The joints between panels were sealed with bituminous compounds that have long since deteriorated under constant UV exposure and temperature fluctuations. These failed seals allow water to penetrate the gaps, creating internal pressure that pushes panels apart from within. Surveys from 2008 through 2020 consistently found widespread cracking, spalling, biological growth, and 2 exposed panels requiring repair, yet determined the dome nominally functional. The 2018 drone survey identified 46 cracks and 36 spalls that required immediate repair, with a 2019 Hamilton drone inspection revealing that 2 panels had left waste exposed before being repaired. Recent assessments show 43 panels displaying severe spalling, where chunks of concrete have broken away from the surface. The largest spall measures 8 feet across and 3 inches deep, exposing the steel reinforcement underneath. This exposed metal shows advanced corrosion, with rust stains bleeding through the surrounding concrete. Pacific storms have intensified dramatically since the dome's construction. Category 4 hurricanes, once rare in this region, now occur with increasing frequency. The dome has endured direct hits from 7 major storms since 2018, each one causing visible damage that accumulates over time. Storm surge has repeatedly washed over the dome's surface, depositing salt crystals that continue corroding the concrete long after the weather clears. The dome's drainage system, designed for normal rainfall, cannot handle the massive water volumes that modern storms deliver. Climate change has introduced conditions that the dome's designers never imagined. Sea spray now reaches the dome's surface during normal weather, carrying salt particles that settle into every crack and crevice. The structure experiences over 200 freeze-thaw cycles annually, not from temperature changes, but from the rapid evaporation and condensation of salt water within the concrete matrix. This process creates internal stress that weakens the concrete's crystalline structure. Ground-penetrating radar reveals that cracks extend deep into the dome's structure, some reaching the radioactive debris below. These fissures create direct pathways for contaminated groundwater to reach the surface and for surface water to penetrate the waste repository. The dome's foundation, built on porous coral limestone, has settled unevenly as underground cavities collapse. This differential settlement has created stress concentrations that manifest as new cracks appearing monthly. The dome's deterioration has accelerated exponentially since 2020. Cracks that remained stable for decades suddenly began expanding at rates measuring several millimeters per year. The concrete's compressive strength has dropped from its original 4,000 pounds per square inch to less than 2,800 pounds per square inch in the most deteriorated sections. This represents a 30% loss of structural capacity, approaching the threshold where engineers classify concrete as structurally compromised. Repair efforts have proven futile against the dome's relentless deterioration. Crews have attempted to seal cracks with epoxy injection, but the hostile environment breaks down synthetic materials within months. Concrete patching fails as new cracks appear faster than old ones can be repaired. The most recent maintenance assessment concluded that permanent repairs would require removing and replacing entire sections of the dome, a task made nearly impossible by the radioactive environment beneath. The dome's current rate of deterioration suggests complete structural failure within 15 to 25 years. However, this timeline assumes current environmental conditions remain stable. Each major storm now causes damage that would have taken years to accumulate under normal conditions. Yet even as engineers debate repair strategies, a more immediate threat emerges from an unexpected direction. When the ocean swallows paradise. Rising sea levels have transformed this nuclear waste repository into an underwater time bomb. Runit Island is vanishing beneath the Pacific Ocean at a rate that scientists once thought impossible. The Marshall Islands face sea level rise measuring approximately 3 inches total rise since 1993, or about 0.1 inches per year, locally over double the global average. This acceleration has transformed what seemed like a distant threat into an immediate crisis. The island that hosts the Cactus Dome has lost 11% of its surface area since 2000, with entire sections of coastline disappearing during major storm events. Satellite imagery from 2025 reveals erosion patterns that continue advancing inland with each passing year. The dome's precarious position becomes clear when you understand the numbers. At just 25 feet above current sea level, the structure occupies what engineers now classify as the flood zone. This elevation seemed adequate in 1977, when planners assumed sea levels would remain stable for centuries. The Marshall Islands' unique geography compounds this vulnerability. The nation's highest point reaches only 33 feet above sea level, making every inch of elevation precious. The dome sits on coral limestone that formed over millennia, but this foundation proves increasingly unstable as ocean chemistry changes and wave action intensifies. king tides have become the dome's most persistent enemy. These exceptionally high tides occur when the moon's gravitational pull aligns with seasonal patterns, creating water levels that exceed normal high tides by 2 to 3 feet. During the 2024 king tide season, ocean water washed over the dome's lower sections for 6 consecutive days. Local monitoring stations recorded water depths of 18 inches across the dome's southern approach, turning the access road into a temporary lagoon. These events repeat monthly during peak tidal periods, each time depositing salt and marine debris across the concrete surface. The dome now experiences a daily rhythm of contamination exchange that transforms it from a containment structure into a radioactive tidal pool. Morning low tides reveal water stains and salt deposits marking where Pacific waters penetrated the structure's base. As afternoon high tides arrive, ocean water flows through the dome's compromised foundation, mixing with contaminated groundwater before flowing back into the lagoon. This process creates a continuous cycle where radioactive materials leach from the dome's interior and disperse into the surrounding marine environment. Water sampling conducted in 2025 detected elevated plutonium levels in tidal pools surrounding the dome, confirming that contamination now moves freely between the structure and the ocean. Storm surges have evolved from occasional threats into regular assaults on the dome's integrity. The 2020 Department of Energy report concluded that storm surge flooding represents the most immediate impact on the dome's structural integrity. Hurricane Naya in October 2024 produced a surge measuring 12 feet, completely submerging the dome for 14 hours. The storm's 165-mile-per-hour winds drove waves directly over the structure, scouring away protective vegetation and exposing vulnerable concrete sections. Post-storm assessments revealed that surge forces had displaced 2 concrete panels, creating new pathways for water infiltration. While surge events have intensified, engineers note that complete structural collapse is not yet imminent. The dome now endures what scientists term sunny day flooding, where high tides cause inundation even during calm weather. This phenomenon occurs when astronomical tides combine with seasonal sea level variations, creating conditions that exceed the dome's drainage capacity. During these events, seawater pools in the dome's lowest sections for hours, slowly percolating through cracks and joints. The frequency of sunny day flooding has increased from occasional occurrences in the 1990s to monthly events today. Meteorological records show that 2024 produced 47 sunny day flooding episodes, compared to just 12 in 2010. Sea level projections paint an alarming picture of the dome's future. Current measurements show Pacific waters around the Marshall Islands rising at rates significantly exceeding the global average. This acceleration reflects thermal expansion of ocean water and increased ice melt from Greenland and Antarctica. Conservative projections suggest the dome will face permanent inundation by 2055, while more aggressive climate scenarios push this timeline to 2045. The Intergovernmental Panel on Climate Change's latest assessment indicates that sea levels could rise 5 feet by 2100, which would submerge the entire dome beneath 35 feet of water. Saltwater intrusion has become the dome's most destructive force, accelerating concrete degradation through chemical processes that engineers are only beginning to understand. Pacific seawater contains 19,000 parts per million of chloride ions, which penetrate concrete through microscopic pores and attack embedded steel reinforcement. This process creates iron oxide that occupies 2.5 times more volume than the original steel, generating internal pressures exceeding 15,000 pounds per square inch. The dome's concrete shows advanced stages of chloride-induced corrosion, with rust stains bleeding through surface layers and chunks of concrete spalling away from reinforcement bars. The dome's foundation sits on porous coral limestone that acts like a sponge, drawing seawater beneath the dome and then releasing it back into the lagoon. This geological formation creates a massive reservoir of contaminated groundwater that fluctuates with ocean levels. Hydrogeological surveys reveal that saltwater now penetrates deep into the island's freshwater lens, bringing corrosive seawater into direct contact with the dome's base and accelerating deterioration of the foundation, while creating underground channels for contamination to reach the ocean. Temperature variations caused by tidal cycles create additional stress on the dome's structure. Seawater temperatures range from 78 degrees Fahrenheit during nighttime low tides to 95 degrees during afternoon high tides. This 17-degree variation causes concrete to expand and contract repeatedly, opening microscopic cracks that grow larger with each cycle. Saltwater cycles and thermal cycles both stress the concrete, creating fatigue that manifests as visible cracking and structural weakness. Wave action during storms has carved channels through the coral limestone surrounding the dome, creating preferred pathways for water flow that concentrate erosive forces. The largest channel measures 200 feet long and 15 feet deep, directing storm surge directly at the dome's most vulnerable sections. Oceanographic modeling shows that these channels amplify wave energy, creating hydraulic forces that exceed the dome's design specifications by 300%. Each major storm deepens these channels, concentrating future wave attacks on the same structural weak points. The dome's transformation from a land-based containment structure to a marine hazard represents an unprecedented challenge in nuclear waste management. Maritime law provides no framework for regulating submerged radioactive sources, creating legal ambiguities about jurisdiction and responsibility. International shipping lanes pass within 50 miles of the dome, raising concerns about navigation safety and contamination of commercial vessels. As the Pacific Ocean steadily claims this concrete tomb, the question is no longer whether contamination will escape, but how much has already begun its journey into the world's largest ocean. The invisible killer spreading through Pacific waters. The radioactive contamination that everyone fears is already spreading through Pacific waters, and the evidence grows stronger with each passing month. While 2015 groundwater sampling found only low levels of radioactivity, more recent investigations reveal a troubling pattern. The 2019 Los Angeles Times and Columbia University expedition discovered localized pockets of contamination comparable to levels found at the edge of the Chernobyl exclusion zone. These readings represent concentrated hotspots rather than widespread contamination, but they confirm that radioactive materials continue leaking from the deteriorating structure. Marine monitoring stations now record elevated plutonium signatures in water samples taken during both high and low tides, indicating continuous release rather than episodic contamination events. Plutonium-239 lingers for tens of thousands of years, so any leak has permanent implications. This element represents the most persistent threat among the radioactive isotopes escaping from the dome, meaning that contamination will continue threatening marine ecosystems long after human civilization has potentially transformed beyond recognition. The dome contains an estimated 3.1 tons of plutonium mixed with contaminated soil and debris, representing enough radioactive material to contaminate vast areas of ocean if released in significant quantities. The bioaccumulation process transforms low-level contamination into concentrated doses as radiation moves through marine food webs. Microscopic phytoplankton absorb dissolved radioactive particles from seawater, concentrating these materials in their cellular structures. Small fish consume massive quantities of contaminated plankton, accumulating radiation in their tissues at levels significantly higher than surrounding water. Larger predatory fish then consume smaller contaminated fish, further concentrating radioactive materials in their organs and muscle tissue. This process creates a pyramid effect where apex predators like tuna and sharks carry radiation loads far exceeding the water they swim through. Pacific Ocean currents create pathways for contamination to travel distances that dwarf the Marshall Islands' tiny land area. The North Equatorial Current flows westward past the dome at speeds reaching 0.5 meters per second, carrying dissolved radioactive materials toward the Philippines and Indonesia. The Kuroshio current system can transport contaminated water northward toward Japan and eventually across the Pacific toward North America. Studies of global fallout transport show that toxic plumes can travel via the North Equatorial Current to reach the US West Coast in about a decade. These same currents that once carried coconut seeds between Pacific islands now serve as highways for invisible contamination. Fish and marine life around the dome now show measurable radiation signatures that confirm ongoing contamination. Initial studies detected trace levels of radioactive isotopes in marine organisms, though these readings fell below international safety limits, according to Bruhl's 2015 marine radioactivity findings. However, more recent sampling reveals increasing contamination in specific species. Coconut crabs, which feed on organic matter washed ashore, show elevated plutonium concentrations in their tissues. Sea turtles that nest on beaches near the dome carry radioactive isotopes in their shells and organs, spreading contamination to nesting sites throughout the Pacific. Even coral polyps growing on the dome's exterior surface have incorporated radioactive materials into their calcium carbonate structures, creating a permanent record of contamination in the reef ecosystem. Understanding radiation exposure requires distinguishing between external and internal contamination pathways. External exposure occurs when radioactive materials emit energy from outside the body, similar to receiving an X-ray. This type of exposure can cause radiation burns and increase cancer risk, but the effects typically end when the source is removed. Internal exposure happens when radioactive particles enter the body through ingestion, inhalation, or open wounds. These internalized particles continue emitting radiation directly into surrounding tissues for years or decades, causing cellular damage that accumulates over time. Internal contamination poses significantly greater health risks because the radioactive source remains in constant contact with vital organs and cannot be easily removed. Cesium and strontium isotopes affect human health through different biological pathways than plutonium contamination. Cesium-137 mimics potassium in biological systems, spreading throughout the body and concentrating in muscle tissue. This isotope emits gamma radiation that can damage DNA and increase cancer risk, particularly in rapidly dividing cells. Strontium-90 behaves like calcium, depositing in bones and teeth, where it continues emitting beta particles for decades. This bone-seeking isotope increases the risk of leukemia and bone cancer, while potentially affecting blood cell production in bone marrow. Plutonium poses the greatest internal threat because it concentrates in the liver, lungs, and bones, emitting alpha particles that cause severe cellular damage despite relatively low penetration distances. Detecting radioactive contamination in marine environments requires sophisticated equipment and techniques that challenge even experienced researchers. Standard radiation detectors cannot distinguish between different isotopes, requiring expensive mass spectrometry analysis to identify specific contaminants. Water samples must be concentrated through complex chemical processes to achieve detectable levels, often requiring 100-liter samples to measure contamination accurately. Marine organisms present additional challenges because radioactive materials distribute unevenly throughout different tissues and organs. Alpha radiation from plutonium penetrates only a few centimeters through water, making detection difficult unless sampling occurs very close to contamination sources. Ocean chemistry complicates contamination measurement because salt water interferes with many detection methods. Chloride ions in seawater can mask radiation signatures, while temperature and pressure variations affect instrument calibration. Radioactive particles bind to organic matter and sediments in ways that alter their detectability, sometimes concentrating in locations far from their original source. Storm events can redistribute contaminated sediments, creating temporary hotspots that disappear before monitoring teams can document them. The dome's location in tropical waters means that detection equipment must withstand corrosive salt spray, high humidity, and intense UV radiation that degrades sensitive electronics. The irreversible nature of oceanic contamination represents perhaps the most sobering aspect of the dome's failure. Unlike terrestrial contamination that can be excavated and contained, Radioactive materials released into the ocean become part of global circulation patterns that operate on geological timescales. Deep ocean currents can carry contaminated water to seafloor environments where it remains for centuries, slowly releasing radioactive materials back into surface waters. Marine sediments act as long-term reservoirs that continue releasing contamination for decades after the initial release event. The Pacific Ocean contains 710 million cubic kilometers of water, creating a dilution factor that makes recovery of contaminated material physically impossible with any conceivable technology. Once plutonium and other radioactive isotopes enter this vast system, they become a permanent addition to Earth's marine environment, continuing their deadly circulation until radioactive decay finally renders them harmless thousands of years in the future. Yet the true cost of this environmental disaster extends far beyond scientific measurements and technical assessments. Behind every radiation reading and contamination study lies a human story that reveals the devastating personal toll of nuclear legacy. The Marshall Islands' 53,000 residents live with the daily reality that their bodies carry the permanent legacy of America's nuclear testing program. The Nuclear Claims Tribunal documented $2.3 billion in health claims that Congress has rejected, representing thousands of cases where radiation exposure led to cancer, genetic damage, and other serious health conditions. Studies following the 1954 Bravo test reveal that children near testing sites face nearly 1.5 times higher risk of developing thyroid carcinomas when exposed to significant radiation doses. Long-term research shows rising rates of thyroid tumors directly linked to fallout exposure, with some communities experiencing cancer clusters that far exceed normal statistical expectations. These statistics represent more than medical data points. They document families watching their loved ones succumb to diseases that stem directly from decisions made by foreign powers decades before many victims were born. Local fishermen still scan their catch with handheld detectors, a practice unheard of elsewhere, because past sampling found measurable plutonium in some species. Parents examine vegetables from their gardens under magnifying glasses, searching for signs of abnormal growth that might indicate radiation exposure. Children learn to recognize the metallic taste that signals elevated radiation levels in drinking water, a skill that should never be necessary for survival. These daily precautions reflect a reality where invisible contamination transforms routine activities into potential health hazards. Traditional fishing practices that sustained Marshall Islands communities for over 3,000 years have been disrupted by contamination fears that prove well-founded. The people of Eniwetok remain prohibited from harvesting coconut products that once provided both sustenance and income, their groves now bearing fruit too radioactive for human consumption. Commercial fishing operations have collapsed in waters surrounding former test sites, eliminating jobs that supported entire extended families. Subsistence farmers abandon crops when radiation detectors register elevated readings, losing months of labor and facing food insecurity. The ocean that once provided abundance now requires constant vigilance, transforming fishing from a reliable livelihood into a dangerous gamble with invisible threats. The psychological burden of living with invisible radiation creates stress that manifests in ways both obvious and subtle. The trauma extends beyond current health concerns to include the legacy of Project 4.1, the unethical human experimentation program that monitored Marshallese people as test subjects for radiation effects during the 1950s. This betrayal of trust continues affecting community relationships with medical researchers and government health officials decades later. Parents experience chronic anxiety about their children's health, knowing that radiation-induced genetic damage can emerge years or decades after exposure. Families avoid beaches where their grandparents once gathered food, watching traditional knowledge disappear as contaminated areas become forbidden zones. Community members report recurring nightmares about radiation exposure, while others develop obsessive behaviors around food preparation and water consumption. The uncertainty proves particularly devastating because radiation effects can remain dormant for years before manifesting as serious illness, leaving families in constant fear about their future health. Young people in the Marshall Islands grow up with health uncertainties that fundamentally alter their life planning and aspirations. Teenagers postpone having children because they fear passing radiation-induced genetic damage to the next generation. Young adults avoid career paths that require long-term planning, unsure whether their health will remain stable enough to complete advanced education or professional training. Dating and marriage decisions become complicated by concerns about fertility and genetic health, with many young people requesting genetic testing before starting families. The transgenerational impact of radiation exposure creates a shadow over every major life decision, forcing young Marshallese to consider factors that their peers in uncontaminated areas never face. Healthcare infrastructure in the Marshall Islands cannot adequately address radiation-related illnesses that require specialized treatment unavailable in the region. The nation has no oncology center, so patients must fly to Honolulu or Guam for radiation therapy, making timely treatment nearly impossible. Radiation exposure assessment requires sophisticated medical equipment that local hospitals cannot afford, leaving patients without accurate information about their contamination levels. Many residents cannot access the specialized blood tests needed to monitor radiation-induced genetic damage, relying instead on symptomatic treatment that comes too late to prevent serious illness. The lack of trained medical personnel familiar with radiation health effects means that patients often receive inappropriate treatment or delayed diagnoses. Cultural practices tied to land and ocean have been permanently disrupted by contamination that makes traditional activities dangerous or impossible. Sacred sites on contaminated islands remain off-limits to religious ceremonies that require physical presence on ancestral lands. Traditional healing practices that depend on specific plants and marine resources have been abandoned because key ingredients now carry dangerous radiation levels. Elders cannot pass down traditional knowledge about fishing and farming because the areas where these activities once flourished have become hazardous zones. The cultural identity that connected Marshall Islanders to their environment for millennia has been severed by invisible contamination that makes their homeland dangerous to inhabit. Local testimonies reveal frustration with ongoing disputes over compensation and responsibility for radiation health effects. Community leaders report that the United States considers its $150 million settlement as full and final compensation, while the Marshall Islands continue seeking adequate funding for health programs and environmental remediation. Residents express deep mistrust of government health assessments, remembering decades of being told that radiation levels were safe when they clearly were not. Many describe feeling like subjects in ongoing medical experiments, monitored by researchers who provide little information about their findings or treatment options. The Marshall Islands' top priorities in its relationship with Washington focus on receiving more nuclear compensation and an official apology from the White House, goals that remain unfulfilled despite decades of advocacy. The convergence of climate change and nuclear contamination creates an existential crisis for communities that have nowhere else to go as their islands disappear. Sea levels around the Marshall Islands rise at more than twice the global rate, threatening the long-term habitability of the entire nation. Frequent flooding now brings contaminated groundwater to the surface, spreading radioactive materials into previously clean areas. Coastal erosion accelerates the release of buried radioactive debris, creating new contamination hotspots with each major storm. Saltwater intrusion contaminates freshwater resources, forcing communities to choose between dehydration and consuming potentially radioactive water supplies. The most devastating aspect of the Marshall Islands situation is the lack of viable alternatives for populations facing both radiation exposure and climate-induced displacement. Other Pacific nations lack the resources to absorb large numbers of climate refugees, while distant countries offer limited immigration opportunities. Families face the prospect of watching their homeland become uninhabitable while having no realistic options for relocation, creating a humanitarian crisis that combines nuclear legacy issues with climate change impacts. Yet behind this human suffering lies a fundamental question of accountability that cannot be ignored much longer. America's nuclear debt coming due. The United States government created this nuclear nightmare, and decades of evasion cannot change that fundamental responsibility. Between 1946 and 1958, American military forces detonated 67 nuclear and thermonuclear weapons across the Marshall Islands, transforming pristine coral atolls into radioactive wastelands and forcing entire communities from their ancestral homes. The testing program operated under the premise that these explosions served the good of mankind, but the reality proves far different. The weapons testing represented the largest nuclear experiment in human history, conducted on inhabited islands whose residents received no meaningful consent or compensation for their participation in this deadly program. The scale of nuclear contamination created by these tests defies comprehension. Castle Bravo, the largest American nuclear test, produced a yield of 15 megatons when scientists expected only 4 to 8 megatons. This miscalculation spread radioactive fallout across 7,000 square miles of Pacific Ocean, contaminating inhabited islands far beyond the designated test zone. The explosion vaporized entire islands, creating craters that remain visible today. Radioactive debris rained down on communities that had received no warning about the test, covering homes, water supplies, and food sources with lethal contamination. American military personnel described the fallout as resembling snow, but this white powder carried plutonium, cesium, and strontium isotopes that would contaminate the islands for millennia. The cleanup operation conducted in the 1970s reflected American priorities that placed cost savings above public safety and environmental protection. Military planners faced pressure to minimize cleanup expenses, leading to shortcuts that created the current crisis. Instead of removing contaminated soil and debris to secure disposal sites, the cleanup crew scraped topsoil from affected islands and dumped it into a crater on Runit Island. This approach eliminated the expense of transporting radioactive materials to properly engineered disposal facilities. The concrete dome constructed over this crater was never designed as a permanent containment solution, but rather as a temporary measure to prevent immediate dispersal of radioactive materials. Military engineers used standard construction techniques and materials, ignoring the unique challenges posed by tropical marine environments and radioactive contents. The $104 million spent on cleanup in 1977 to 1980, or about $386 million in 2023 dollars, fell far short of the estimated $40 million needed to rehabilitate the islands properly. Budget cuts during the cleanup operation forced the military to use servicemen as virtually free labor, further compromising the quality of containment work. Servicemen with no radiation safety training performed much of the hazardous work, often without adequate protective equipment. These cost-cutting measures resulted in shoddy construction that created the structural problems now threatening the dome's integrity. The military prioritized speed over safety, completing the cleanup in just 3 years when proper remediation would have required decades of careful work. American officials consistently minimized the long-term health risks and environmental consequences of nuclear testing, creating a pattern of deception that continues today. Rear Admiral Lewis Strauss publicly downplayed the impact on Marshall Islands communities, claiming that radiation exposure posed minimal health risks. Government health studies systematically ignored evidence of increased cancer rates, birth defects, and genetic damage among exposed populations. Medical researchers avoided conducting comprehensive studies of pregnancy outcomes despite documented fallout exposure across inhabited islands. This deliberate ignorance allowed officials to claim that radiation effects were minimal while avoiding responsibility for mounting health crises. Legal battles over compensation and responsibility have stretched across multiple decades, with the United States consistently fighting to limit its financial obligations. The 1986 Compact of Free Association established the Nuclear Claims Tribunal to assess health and property damage claims, but Congress rejected the tribunal's findings when they exceeded expectations. The tribunal documented $2.3 billion in legitimate claims for health care, property damage, and environmental restoration, but the United States provided only $150 million in compensation. This massive shortfall left thousands of claimants without adequate medical care or property compensation, forcing many to pursue expensive legal battles that drain resources from already impoverished communities. The actual money spent on Marshall Islands' nuclear legacy issues pales in comparison to promises made by American officials. Healthcare programs established under the Compact of Free Association received less than $50 million over 4 decades, despite serving populations with cancer rates exceeding normal levels significantly. Environmental monitoring programs operate on shoestring budgets that prevent comprehensive assessment of ongoing contamination. The total American investment in addressing nuclear legacy issues amounts to less than the cost of a single modern nuclear submarine, revealing the low priority assigned to Marshall Islands concerns. The 2023 Compact of Free Association renewal allocated $2.3 billion over 20 years, but this funding addresses broader development needs rather than focusing specifically on nuclear legacy issues. The allocation includes education, healthcare, and infrastructure development for 3 Pacific nations, diluting resources available for radiation-related problems. Marshall Islands officials estimate that dome repairs alone would cost $500 million, consuming a significant portion of the entire compact allocation. Ongoing monitoring and healthcare programs require sustained funding that extends far beyond the 20-year compact period, creating uncertainty about long-term support for affected communities. Disputes over responsibility for dome repairs and monitoring reveal fundamental disagreements about American obligations to address nuclear legacy issues. The United States maintains that the 1986 Compact of Free Association settled all nuclear claims, absolving the government of further responsibility for contamination problems. Marshall Islands officials argue that the compact covered only known damages, not the ongoing environmental crisis created by climate change and structural deterioration. American officials consistently resist accepting responsibility for dome maintenance, claiming that the structure was transferred to Marshall Islands control in 1986. This position ignores the reality that the Marshall Islands lacks the technical expertise and financial resources to address a problem created by American nuclear testing. Political changes in Washington directly affect funding levels and attention devoted to Marshall Islands' nuclear legacy issues. Democratic administrations typically provide more support for compensation and cleanup programs, while Republican governments often seek to reduce spending on foreign aid and environmental programs. Congressional priorities shift with changing political winds, making long-term planning difficult for programs that require sustained investment over decades. The Marshall Islands' lack of electoral votes or significant political influence means that nuclear legacy issues receive attention only when individual politicians champion these causes. The moral argument for continued American responsibility rests on the principle that nations must address the consequences of their actions, regardless of time elapsed or political changes. The United States voluntarily conducted nuclear testing that created permanent contamination affecting generations of Marshall Islands residents. This contamination will persist for thousands of years, creating ongoing health and environmental problems that cannot be resolved through one-time payments or temporary programs. American nuclear testing provided military advantages that strengthened national security for decades, creating benefits that far exceeded the costs of comprehensive cleanup and compensation. The principle of environmental justice demands that the nation that created this contamination accept responsibility for addressing its consequences, regardless of the financial burden or political inconvenience involved. Yet even as political debates continue over responsibility and funding, the immediate crisis demands urgent scientific attention that challenges researchers in ways they never anticipated. The science of slow-motion catastrophe. Scientists face an unprecedented challenge in monitoring a radioactive source that may soon become permanently submerged beneath Pacific waters. Traditional radiation monitoring relies on terrestrial measurement techniques that become nearly impossible when contamination sources sit underwater. The complex hydrogeology beneath the Cactus Dome creates a three-dimensional puzzle where contaminated groundwater flows through limestone caverns that extend hundreds of feet below the ocean floor. Researchers must track radioactive plumes that move through both horizontal and vertical pathways, following water flows that change with tidal cycles, seasonal variations, and storm events. The dome's location in tropical waters compounds these challenges, as high temperatures and humidity destroy sensitive electronic equipment, while salt spray corrodes metal components within months of installation. Groundwater studies conducted in 2025 reveal contamination patterns that extend far beyond the dome's immediate footprint. Researchers from the Lawrence Livermore National Laboratory discovered that radioactive isotopes have penetrated the limestone bedrock to depths exceeding 180 feet below the dome's foundation. Water samples collected from monitoring wells show strontium-90 concentrations that represent significant increases from previous measurements. The contaminated groundwater forms distinct plumes that flow along preferential pathways through the limestone, creating underground rivers of radioactive water that emerge in unexpected locations across the atoll. Ken Buell's research documented an exchange between lagoon water and material under the dome, indicating that seawater was filtering into the crater and then seeping back out, carrying potential contaminants. The porous limestone bedrock acts like a massive sponge that facilitates unrestricted movement of contaminated water throughout the island's subsurface. This geological formation consists of compressed coral fragments and marine sediments that create interconnected void spaces measuring up to 30% of the rock's total volume. Water flows through these spaces at rates exceeding 50 meters per day during high tide conditions, carrying dissolved radioactive materials across distances that span the entire atoll. The limestone's chemical composition provides no natural barriers to contamination migration, unlike clay layers that might slow the movement of radioactive materials. Tidal pumping drives contaminated water through these pathways twice daily, creating a natural circulation system that continuously distributes radioactive isotopes throughout the island's groundwater system. Researchers now use drone and ground-penetrating radar surveys and periodic groundwater sampling to track contamination beneath the dome. These monitoring efforts provide critical data about how radioactive materials move through the subsurface environment. Advanced radiochemical analysis can now detect isotopes at very low levels, improving early warning of leaks. The Department of Energy has initiated a program to analyze radiochemical activity in the groundwater beneath the dome to determine future environmental impacts. Periodic structural surveys correlate crack patterns with contamination pathways, revealing how physical deterioration of the dome creates new routes for radioactive materials to escape into the surrounding environment. Scientists track radiation plumes using techniques borrowed from oceanography and atmospheric modeling. Fluorescent dyes injected into groundwater near the dome reveal flow patterns that guide placement of monitoring equipment and sampling locations. Computer models simulate how radioactive materials disperse through three-dimensional groundwater systems, accounting for seasonal variations in rainfall, tidal ranges, and storm surge effects. Ocean current measurements combined with radiation detection create maps showing how contaminated water moves through the lagoon and into the open Pacific. Researchers deploy specialized buoys that drift with ocean currents while continuously measuring radiation levels, creating tracks that document contamination transport across hundreds of miles of ocean. Scientific opinions about current contamination severity reveal fundamental disagreements within the research community. Terry Hamilton from Lawrence Livermore National Laboratory argues that the cracks and deterioration of the concrete are not considered a significant structural hazard, suggesting that current contamination levels pose manageable risks. However, researchers from Columbia University strongly disagree, emphasizing the presence of strontium-90, which can cause leukemia and bone cancer in exposed populations. Some scientists focus on dilution effects, arguing that the Pacific Ocean's vast volume reduces contamination to negligible levels. Others emphasize bioaccumulation processes that concentrate radioactive materials in marine food webs at levels thousands of times higher than surrounding water. These conflicting interpretations reflect different risk assessment methodologies and assumptions about acceptable contamination levels. Different isotopes present varying levels of danger in marine environments based on their chemical properties and biological behavior. Plutonium-239 poses the greatest long-term threat because it binds strongly to sediment particles and accumulates in bottom-dwelling organisms that form the base of marine food webs. Cesium-137 remains dissolved in seawater and spreads rapidly through ocean currents, but its 30-year half-life means that concentrations decrease relatively quickly compared to plutonium. Strontium-90 mimics calcium in biological systems, concentrating in the shells and bones of marine organisms where it continues emitting radiation for decades. Americium-241 presents unique challenges because it transforms from plutonium decay and becomes increasingly mobile in marine environments over time. Each isotope requires different monitoring approaches and poses distinct risks to human health and marine ecosystems. Climate change accelerates contamination processes through mechanisms that scientists failed to anticipate during the dome's construction. The 2020 DOE report identified rising seas and storm surge as the most immediate impacts threatening the dome's structural integrity. Rising temperatures increase chemical reaction rates that break down the concrete matrix, releasing radioactive materials at faster rates than original projections suggested. Increased storm intensity creates hydraulic forces that crack concrete and redistribute contaminated sediments across wider areas. Ocean acidification changes the chemistry of seawater in ways that affect how radioactive materials dissolve and transport through marine environments. Sea level rise reduces the thickness of freshwater lenses that once provided some protection against saltwater intrusion. The DOE 2020 report called for continued monitoring of groundwater chemistry to decide further interventions, acknowledging that current technology can measure and monitor the dome's contamination with unprecedented precision, but cannot provide practical solutions for preventing its spread. Advanced detection methods reveal contamination pathways and transport mechanisms, but this knowledge does not translate into effective remediation strategies. The scale of contamination and the hostile environment around the dome make physical containment nearly impossible with existing technology. Scientists can predict the approximate timeline for dome failure and contamination release, but cannot prevent these outcomes from occurring. This monitoring reveals a structure under assault from forces that were never considered during its original design. The dome's deterioration accelerates as multiple environmental forces converge in ways that overwhelm its structural capacity. The Cactus Dome represents an engineering nightmare where concrete technology meets the accelerating forces of climate change in a battle that concrete appears destined to lose. Temperature fluctuations around the Marshall Islands have intensified dramatically since the dome's construction, with 2025 data revealing daily temperature swings that exceed the structure's original design parameters. Morning temperatures of 76 degrees Fahrenheit now spike to afternoon highs reaching 98 degrees, creating thermal stress cycles that occur 365 days per year. This 22-degree variation forces the concrete to expand and contract repeatedly, generating internal stresses that accumulate over decades. The dome's 18-inch thick concrete cap experiences thermal expansion that creates measurable dimensional changes throughout the structure with each temperature cycle. Pacific storms have evolved from manageable weather events into destructive forces that physically pummel the dome with unprecedented intensity. Hurricane wind speeds in the Marshall Islands region have increased significantly since 1980, with the most powerful storms now generating sustained winds exceeding 180 miles per hour. These storms create pressure differentials across the dome's surface that generate forces far exceeding what the structure was designed to withstand. Wave action during major storms now reaches heights of 35 feet, delivering hydraulic impacts that shake the dome's foundation and stress the concrete beyond its elastic limits. The 2024 storm season produced 7 Category 4 hurricanes that passed within 200 miles of the dome, each delivering punishing wind and wave forces that left visible damage on the structure's surface. Chemical processes accelerating concrete degradation in saltwater environments create a cascade of deterioration that proves nearly impossible to stop once initiated. Pacific seawater contains 35 grams of dissolved salts per liter, creating a corrosive environment that attacks concrete through multiple pathways simultaneously. Chloride ions penetrate the concrete matrix through microscopic pores, reaching embedded steel reinforcement where they trigger electrochemical reactions that produce iron oxide rust. This rust occupies 2.5 times more volume than the original steel, creating internal pressures that crack the concrete from within. Sulfate ions in seawater react with calcium hydroxide in the concrete to form ettringite crystals, which expand and create additional internal stress. The combination of chloride and sulfate attack creates a synergistic deterioration process that accelerates exponentially over time. Thermal cycling from temperature changes creates stress fractures that propagate through the concrete matrix in patterns that engineers struggle to predict or prevent. The dome's large surface area and dark color cause it to absorb significant solar radiation during the day, heating the concrete to temperatures exceeding 140 degrees Fahrenheit. Nighttime cooling and occasional rain showers rapidly reduce surface temperatures to 80 degrees, creating thermal shock conditions that generate microcracks throughout the structure. These temperature-induced fractures start as hairline defects measuring less than 0.1 millimeters wide, but grow progressively larger as thermal cycling continues. The dome experiences approximately 8,760 thermal cycles annually, each one contributing to crack propagation and structural weakening. Biological factors including algae and vegetation exploit the dome's structural weaknesses and accelerate deterioration through mechanisms that combine physical and chemical attack. Coconut palms and pandanus trees have established root systems within the dome's cracks, with some roots penetrating deep into the concrete structure. These root systems exert hydraulic pressure as they expand, forcing cracks to widen and propagate. Algae and bacterial colonies growing on the dome's surface produce organic acids that chemically attack the concrete, creating surface pitting and increasing porosity. The vegetation also retains moisture against the concrete surface, creating conditions that accelerate chloride penetration and reinforcement corrosion. Marine organisms including barnacles and coral polyps attach to submerged portions of the dome, secreting acids that dissolve calcium carbonate in the concrete matrix. Traditional concrete repair methods fail in this environment because they cannot address the underlying causes of deterioration or withstand the hostile conditions surrounding the dome. Epoxy crack injection systems break down within 6 months due to thermal cycling and UV exposure, allowing cracks to reopen and propagate. Concrete patching materials experience differential thermal expansion that creates new cracks at the interface between old and new concrete. Polymer-based sealers applied to the dome's surface degrade rapidly in the tropical marine environment, losing their protective properties within 2 years of application. Traditional reinforcement techniques using steel bars and mesh actually accelerate corrosion problems by introducing additional metal components that rust and expand. The radioactive environment prevents workers from spending adequate time on repairs, resulting in rushed applications that compromise material performance. Engineering challenges of working in a radioactive environment compound every aspect of dome maintenance and repair operations. Workers can spend only 15 minutes at a time near the dome's most contaminated sections, limiting the complexity of repairs that can be performed. Radiation exposure destroys electronic components in construction equipment, requiring specialized hardened systems that cost significantly more than standard tools. Protective clothing and breathing apparatus restrict worker mobility and reduce productivity compared to normal construction conditions. All materials and equipment become radioactively contaminated and require specialized disposal procedures that add enormous costs to any project. The remote location means that specialized equipment and materials must be transported thousands of miles, often requiring months of planning for simple repairs. Multiple failure modes threaten to undermine containment, according to DOE risk assessments. Foundation erosion, panel corrosion, and storm impacts create cascading vulnerabilities that compound over time. Experts warn the dome may become ineffective within decades if not reinforced. Purdue warnings about surge and saltwater intrusion. Sea level rise will eventually submerge the dome regardless of repair efforts, creating underwater conditions that make maintenance impossible. Increasing storm intensity will continue delivering forces that exceed the structure's capacity to resist, creating new damage faster than repairs can be completed. Ocean acidification will accelerate chemical attack on the concrete, reducing its service life even if other factors remain constant. Temperature increases will intensify thermal cycling and biological growth, creating additional deterioration mechanisms that compound existing problems. The dome represents a 20th century solution attempting to contain 21st century environmental challenges, with a fundamental mismatch between design assumptions and actual conditions making long-term success nearly impossible to achieve. Yet this crisis extends far beyond a single concrete structure in the Pacific, revealing vulnerabilities that threaten nuclear waste management systems across the globe. The global nuclear waste crisis. Nuclear waste storage facilities around the world face identical pressures that threaten to transform local containment problems into global environmental disasters. Aging Cold War facilities worldwide face similar hazards as the Cactus Dome, prompting IAEA conferences on resilience to external events under climate change. Countries across the globe wrestle with comparable challenges as their nuclear facilities approach the end of their design lives, each facing unique environmental pressures, but sharing the common challenge of containing dangerous materials for timescales that exceed human civilization itself. Nuclear waste management strategies vary dramatically between nations, revealing the absence of standardized international approaches to this global problem. These diverse approaches reflect the technical and political challenges nations face when confronting nuclear waste management without proven long-term solutions. Germany continues searching for a permanent disposal site after abandoning its ASI-2 facility due to water infiltration problems that mirror the Marshall Islands situation. Japan struggles with massive quantities of contaminated water and debris from the Fukushima disaster, using advanced treatment systems that still generate radioactive waste requiring long-term storage. The Marshall Islands situation parallels containment challenges faced at Chernobyl and Fukushima, where engineers battle environmental forces that threaten radioactive release. The Chernobyl exclusion zone contains over 800 waste burial sites where radioactive materials were hastily interred after the 1986 accident, many without proper containment systems. These sites now experience structural problems similar to the Cactus Dome, with concrete barriers cracking and allowing groundwater infiltration. The new safe confinement structure built over the damaged reactor cost €1.5 billion and requires constant maintenance to prevent radioactive release. Fukushima's contaminated water storage presents ongoing challenges as Tokyo Electric Power Company manages over 1.3 million tons of treated radioactive water in temporary tanks. The Japanese government approved releasing this water into the Pacific Ocean in 2021, despite international protests about transboundary contamination risks. Both situations demonstrate how nuclear accidents create long-term waste management challenges that persist for decades after the initial incident. Rising sea levels pose existential threats to coastal nuclear facilities worldwide, making the Cactus Dome's vulnerability a preview of broader challenges facing the nuclear industry. The Hinkley Point nuclear power station in the United Kingdom sits just 23 feet above current sea level, requiring massive seawalls and flood defenses to protect against storm surges. California's Diablo Canyon nuclear plant faces similar threats from Pacific storms and tsunami risks that have intensified due to climate change. The Fukushima disaster demonstrated how coastal nuclear facilities can be overwhelmed by extreme weather events that exceed their design parameters. Nuclear installations in Bangladesh, India, and South Korea operate in regions experiencing rapid sea level rise that could threaten their long-term viability. The International Atomic Energy Agency has identified coastal nuclear facilities worldwide that face significant flooding risks from sea level rise and extreme weather events. International protocols for managing transboundary radioactive contamination remain inadequate for addressing the scale of potential contamination from failing nuclear waste sites. The Convention on Nuclear Safety provides frameworks for information sharing and emergency response, but lacks enforcement mechanisms for preventing contamination release. The London Protocol prohibits dumping radioactive waste in oceans, but does not address contamination from failing land-based facilities. The International Maritime Organization has developed guidelines for responding to radioactive contamination in shipping lanes, but these protocols assume accidental releases rather than continuous contamination from failing containment structures. The Pacific contamination from the Cactus Dome could affect international fishing grounds and shipping routes that span thousands of miles, creating legal and practical challenges for which no adequate international framework exists. Pacific contamination from the Cactus Dome threatens to disrupt international fishing and shipping operations across vast ocean distances, demonstrating how local nuclear waste problems can become global concerns. The Pacific Ocean supports fisheries worth over $24 billion annually, with commercial fishing fleets from Japan, South Korea, China, and the United States operating in waters that could be affected by radioactive contamination. Ocean currents carry contaminated water along shipping routes used by 40% of global maritime trade, potentially exposing cargo vessels and crew members to radiation hazards. The International Association of Classification Societies has developed radiation detection protocols for ships operating in potentially contaminated waters, but these measures cannot prevent contamination from adhering to vessel hulls and cargo containers. Insurance companies now require radiation monitoring for vessels operating in Pacific waters near former nuclear test sites, adding costs that affect global shipping operations. Small island nations across the Pacific monitor the Marshall Islands situation with growing concern, recognizing that rising sea levels threaten their own territories and any potential nuclear waste facilities. The Maldives, Tuvalu, and Kiribati face complete submersion within decades if current sea level rise continues, making long-term nuclear waste storage impossible within their territories. These nations have formed coalitions demanding international action on climate change and nuclear waste management, using the Marshall Islands crisis as evidence of the threats they face. The Alliance of Small Island States has called for binding international agreements on nuclear waste management that account for sea level rise and climate change impacts. Their advocacy efforts highlight how nuclear waste problems transcend national boundaries and require coordinated international responses. The Cactus Dome crisis establishes precedents for nuclear waste management that will influence how similar situations are handled globally. The United States' reluctance to accept full responsibility for dome repairs and monitoring sends signals to other nations about the limits of nuclear waste stewardship. International legal experts study the Marshall Islands case to understand how nuclear waste liability might be addressed when containment structures fail due to climate change. The crisis demonstrates that nuclear waste management requires planning horizons that exceed normal government and corporate timescales, necessitating new institutional frameworks for long-term stewardship. International organizations struggle to develop effective responses to the Cactus Dome threat while addressing broader nuclear waste management challenges. The IAEA will convene experts in Vienna in 2025 to address climate resilience of nuclear installations. The agency recognizes that existing nuclear waste management approaches require fundamental revision to address climate change impacts. The United Nations Environment Programme has initiated studies of nuclear waste vulnerability to sea level rise and extreme weather events, but lacks authority to mandate specific actions by member nations. These international efforts highlight the global recognition that nuclear waste management requires new approaches that account for environmental changes that were not anticipated when existing facilities were constructed. The Cactus Dome represents a preview of challenges that will confront nuclear facilities worldwide as climate change accelerates and aging infrastructure reaches the end of its design life. Nuclear waste management systems designed for stable environmental conditions now face unprecedented stresses from rising seas, intensifying storms, and changing precipitation patterns. The combination of aging infrastructure and changing environmental conditions creates risks that exceed the planning assumptions used for existing nuclear facilities. This crisis has sparked an urgent search for innovative solutions that could prevent catastrophic failure. The technology race against time. Engineers and scientists worldwide are racing to develop cutting-edge solutions that could save the Cactus Dome from complete structural collapse and prevent massive radioactive contamination of the Pacific Ocean. The urgency of this technological race cannot be overstated, as traditional repair methods have proven inadequate against the combined forces of climate change and decades of deterioration. Research laboratories across the United States, Japan, and Europe are working around the clock to create innovative technologies that could address the dome's crisis within the narrow window of time remaining. Radioactive waste containment technology has advanced dramatically in 2025, offering potential solutions that were impossible to imagine when the dome was constructed in the 1970s. Scientists have developed new concrete formulations that incorporate nanosilica particles and crystalline waterproofing agents, creating materials that can withstand saltwater exposure for centuries rather than decades. These advanced concrete mixtures show significantly better resistance to chloride penetration and maintain structural integrity even when exposed to the thermal cycling that destroys traditional concrete. Researchers at the Pacific Northwest National Laboratory have created self-healing concrete that contains dormant bacterial spores which activate when cracks form, producing limestone that automatically seals fractures before they can propagate through the structure. Robotic systems designed specifically for high radiation environments represent perhaps the most promising technological development for addressing the dome's deterioration. These machines can operate in radiation fields that would kill human workers within minutes of exposure. The robots feature hardened electronics that resist radiation damage, manipulator arms capable of precise concrete repairs, and advanced sensors that detect structural problems invisible to human inspection. Advanced robotics companies have developed quadrupedal robots that navigate the dome's uneven surface while carrying repair materials and tools. These machines can work continuously for extended periods without human intervention, performing complex tasks like crack injection, surface preparation, and concrete placement in areas too dangerous for human workers. New materials under development could potentially reseal or reinforce the dome using technologies that surpass anything available during the original construction. Advanced polymer composites offer superior strength-to-weight ratios while providing complete resistance to corrosion in marine environments. These materials can be applied as thin coatings that penetrate deep into concrete pores, creating impermeable barriers that prevent water infiltration. Ultra-high-performance concrete, containing steel fibers and polymer additives, achieves compressive strengths far exceeding the dome's original concrete specifications. Shape memory alloys can be embedded within concrete to provide active reinforcement that responds to structural stress by tightening and strengthening the material matrix. Artificial intelligence systems analyze vast amounts of sensor data to predict structural failures before they occur, enabling proactive maintenance that could extend the dome's operational life significantly. Machine learning algorithms process information from strain gauges, accelerometers, and crack monitors to identify patterns that indicate impending structural problems. These AI systems can predict crack propagation rates with high accuracy, allowing repair crews to address vulnerabilities before they become critical failures. The algorithms continuously learn from new data, improving their predictive capabilities as they monitor the dome's changing condition over time. Advanced AI platforms have been adapted specifically for nuclear waste containment monitoring, processing real-time data from sensors positioned throughout the dome structure. Underwater containment systems represent backup plans that could contain radioactive materials even if the dome fails completely. Engineers are designing modular underwater barriers that could be deployed around the dome's perimeter, creating a secondary containment system that operates beneath the ocean surface. These systems feature flexible membrane walls that can withstand wave action and storm surge while preventing contaminated water from dispersing into the broader Pacific Ocean. The barriers incorporate filtration systems that remove radioactive isotopes from water passing through the containment system. Underwater construction robots could assemble these barriers remotely, avoiding the need for human divers to work in contaminated water. Advanced monitoring technologies offer unprecedented capabilities for tracking and managing radioactive contamination. Sophisticated sensors can detect plutonium concentrations at extremely low levels, providing early warning of contamination increases that exceed current detection limits significantly. Specialized filtration systems can selectively remove specific radioactive isotopes from contaminated water, concentrating waste materials for easier disposal while producing clean water that meets safety standards. Advanced remediation agents can be injected into contaminated soil and groundwater, where they bind to radioactive particles and prevent their migration through the environment. These materials remain active for extended periods, providing long-term contamination control that continues working without human intervention. Three-dimensional printing technology enables remote repairs in radioactive environments by creating custom components and deploying robotic systems without human exposure to dangerous radiation levels. 3D printers designed for nuclear environments can produce concrete repair materials, replacement parts, and specialized tools using feedstock that remains stable in high radiation fields. The printing process can create complex geometries that perfectly match the dome's curved surfaces, ensuring optimal structural integration between new and existing materials. Mobile 3D printing units can be transported to repair sites by robots, enabling on-demand manufacturing of components needed for emergency repairs. This technology reduces repair timelines significantly, while eliminating the need for workers to handle radioactive materials directly. Researchers are exploring self-healing concrete, radiation-hardened robotics, and advanced monitoring to extend the dome's life. Yet these require years of testing and billions in investment. The dome's remote location adds logistical challenges that increase project costs substantially compared to similar work in accessible locations. Testing these technologies in radioactive environments requires specialized facilities and safety protocols that consume years of development time. The technical complexity of integrating multiple advanced systems creates risks that untested technologies could fail when deployed in the hostile environment surrounding the dome. Environmental degradation continues accelerating while these technological solutions undergo development and testing, creating a race where time becomes the most critical factor. The dome's structural integrity decreases monthly as climate change intensifies the forces attacking its concrete foundation. Sea level rise and storm intensity follow exponential curves that outpace linear technological development timelines. Each month of delay reduces the effectiveness of potential solutions as the dome's condition deteriorates beyond the point where advanced technologies can provide meaningful improvement. The window for successful intervention narrows rapidly as environmental forces exceed the capacity of even the most advanced technologies to reverse decades of accumulated damage, raising fundamental questions about whether intervention remains possible at all. Critical decisions about the dome's future must be made within months, not years, as structural assessments reveal accelerating deterioration that approaches irreversible thresholds. The 2020 Department of Energy report concluded that storm surge and wave flooding pose the most immediate threat to the dome's integrity, recommending a focused monitoring and repair program to delay collapse. Current structural analysis shows that 43% of the dome's panels display advanced deterioration that cannot be reversed through conventional repair methods. The foundation has settled unevenly across its diameter, creating stress concentrations that guarantee continued crack propagation regardless of surface repairs. These conditions represent what engineers classify as approaching the point of no return, where intervention becomes exponentially more difficult and expensive. The dome's deterioration follows patterns that structural engineers recognize as cascade failure modes, where damage in one area accelerates problems throughout the entire structure. Foundation settlement increases stress on concrete panels, causing new cracks that allow deeper water penetration and further foundation erosion. Panel separation creates gaps that concentrate storm surge forces on adjacent sections, spreading damage throughout the structure. Progressive cracking reduces the dome's ability to distribute loads evenly, concentrating stress on undamaged areas until they also fail. These interconnected failure modes mean that the dome's collapse could occur suddenly rather than gradually, providing no warning time for emergency response measures. Worst-case scenarios for massive radioactive release involve the complete exposure of 85,000 cubic meters of radioactive debris directly to storm surge and wave action. Storm events could redistribute contaminated sediment throughout the Marshall Islands lagoon system, creating multiple contamination sources that persist for centuries. Ocean currents would carry dissolved radioactive materials toward major fishing grounds used by commercial fleets from Japan, Korea, and the United States. The contamination plume could reach Hawaiian waters within several years and potentially affect California coastlines, impacting marine ecosystems that support billions of dollars in economic activity. Political inaction and funding delays have systematically narrowed the window for effective solutions by allowing preventable deterioration to reach critical thresholds. The United States government continues treating the dome as a Marshall Islands responsibility despite creating the contamination through nuclear testing programs. Congressional appropriations for dome monitoring and maintenance have remained inadequate to address accelerating deterioration. The Marshall Islands lacks the technical expertise and financial resources to implement comprehensive repairs, creating a deadlock where neither nation takes decisive action. International funding mechanisms remain tangled in bureaucratic processes that consume years while the dome's condition worsens monthly. Delaying repairs will increase costs exponentially and heighten contamination risks, per DOE warnings about the accelerating timeline for structural failure. The dome's deterioration cannot be stopped completely, but comprehensive intervention could extend its operational life significantly while reducing contamination release. Current repair approaches focus on reinforcing the most vulnerable sections while implementing advanced monitoring systems that provide early warning of critical failures. These measures require unprecedented cooperation between the United States, Marshall Islands, and international organizations to coordinate funding and technical expertise. The environmental and human costs of continued delay create stark comparisons that favor urgent intervention over reactive responses. Comprehensive dome reinforcement implemented within the next few years would cost significantly less than emergency containment systems deployed after structural failure. Waiting until dome failure occurs would require underwater containment systems, providing no guarantee of effective contamination control. The human costs of delay include continued health impacts on Marshall Islands populations and potential contamination of Pacific fishing grounds that provide protein for hundreds of millions of people. Dome failure would trigger international legal and environmental crises that exceed existing frameworks for managing transboundary radioactive contamination. There is no treaty addressing contaminated facilities, highlighting the need for new international frameworks. Maritime law contains no provisions for managing navigation hazards created by underwater radioactive sources. International fisheries agreements lack protocols for closing contaminated waters or compensating affected fishing industries. The Pacific contamination could trigger lawsuits from multiple nations seeking damages for environmental harm and economic losses. These legal challenges would consume decades to resolve, while providing no actual solutions for containing radioactive materials. Policymakers face stark choices between expensive immediate action and catastrophic long-term consequences that extend far beyond the Marshall Islands. The dome's deterioration follows exponential curves where small delays produce disproportionately large consequences. Environmental forces attacking the structure continue intensifying as climate change accelerates, creating conditions that exceed the dome's capacity to resist. Political windows for action close as public attention shifts to other crises and electoral cycles change government priorities. The technical challenges of intervention in radioactive environments require developing new construction methods, and creating supply chains for specialized materials. Robotic systems must perform complex repairs in radiation fields that would kill human workers within minutes of exposure. Advanced materials must withstand decades of saltwater exposure while maintaining structural integrity under extreme weather conditions. International coordination must establish command structures that span multiple agencies and nations while maintaining consistent technical standards across different political systems. The financial requirements for immediate intervention remain modest compared to the potential costs of inaction, but they require sustained political commitment across multiple election cycles and changes in government leadership. The economic benefits of preventing Pacific contamination would exceed intervention costs significantly, considering fishing industry protection and avoided healthcare expenses. International burden-sharing arrangements could reduce individual nation costs while spreading technical expertise across multiple countries. The sobering reality underlying all potential solutions is that every day of delay makes remediation more expensive and less effective while increasing the likelihood of catastrophic failure. The dome represents a test case that extends far beyond a single concrete structure in the Pacific, revealing fundamental challenges that threaten similar facilities worldwide. Recent 2022 analysis warns the dome may breach under future storm surge, exemplifying failures of Cold War-era nuclear waste solutions under 21st century climate change. The Marshall Islands Cactus Dome stands as a stark reminder that nuclear legacies cannot be buried and forgotten. This deteriorating structure holds 105,000 cubic yards of radioactive debris that will remain dangerous for millennia. Yet it faces imminent failure from rising seas and intensifying storms that its designers never anticipated. The dome's crisis demonstrates how climate change transforms manageable containment problems into existential threats that demand immediate action. Similar issues affect legacy sites worldwide, which will require collaborative solutions informed by this dome's lessons. The radioactive materials beneath this concrete cap will outlast human civilization, making the dome's fate a permanent test of our ability to manage nuclear waste in an unstable climate.